Welcome to the next part of unit number 2, that is requirements analysis, under which we were actually talking about requirement modeling. And now we will be looking into class based methods for the requirement modeling, which comes under the strategy of object oriented modeling. So, software problems can almost always be characterized in terms of a set of interacting objects, each representing something of interest within a system. Each object becomes a member of a class of objects. Each object is described by its state, the data attribute that describes the object. So all of this can be represented using a class-based requirements modeling method. So why it is so important? So a class-based requirements model makes use of objects drawn from the customer's view of an application or system. So the model depicts a view of the system that is common to the customer. Therefore, it can be readily evaluated by the customer, resulting in useful feedback at the earliest possible time. Later, as the model is refined, it becomes the basis for the software design. Now let us talk about the primitives of the class-based modeling. Class-based modeling represents objects that the system will manipulate, operations that will be applied to the objects to effect the manipulation, relationships between the objects, and collaborations that occur between the classes that are defined. The elements of class-based model include classes, objects, attributes, operations, CRC models, collaboration diagrams, and packages. So we'll see this in details. Now let us talk about how do we identify the analysis classes. By examining the usage scenario developed as part of the requirements model and performing a grammatical parse, we can identify the analysis classes. Classes are determined by underlining each noun or noun phrase and entering it into the simple table. Synonyms should be noted if the class or noun is required to implement a solution, then it is part of the solution space. Otherwise, if a class is necessary just to describe the solution, then it is a part of the problem space. But what should we look for once all of the nouns have been isolated? Once the nouns are being separated out, then we have to follow the process of manifestation of analysis classes. We need to clearly show themselves in one of the following ways. External entities. For example, the other system devices or people that produce or consume information. Things that are the part of information domain for the problem. For example, reports, displays, letters, signals, etc. Occurrences or events that occur within the context of a simple operation. For example, a property transfer or the completion of a series of robot movements. Rules played by the people who interact with the system, that is manager, engineer, salesperson, etc. Organizational units that are relevant to an application, for example a division, group or team. Places that establish the context of the problem and the overall function, like manufacturing floor or loading dock. Structures that define a class of objects or related classes of objects, like sensors, four-wheeled vehicles or computers. As we have already discussed the safe home security function in previous part, then we will as well as we know the whole problem statement, so we will take that as an example and develop analysis classes. So to illustrate how analysis classes might be defined during the early stages of modeling, consider a grammatical parse for a processing narrative for safe home security functions. Take a pause, just go through this, underline the nouns, and then we will compare your answer with this particular illustration. You can see over here the safe home security function, internet, PC, control panel, installation, number, type, master password, systems, telephone numbers, and sensor events. These are all the nouns. Here, take an example of another part of the same safe home security function. Just consider a grammatical parse of this particular paragraph for a processing narrative for safe home security system or function. Please read through the paragraph and underline nouns. We will compare your answers with this particular illustration. Okay, so these are all the nouns. So we will just make use of all these nouns and verbs for developing the analysis classes. We will put all these nouns into a particular table like structure. On the basis of extracted nouns, we can propose number of potential classes. So you can see it over here. The potential classes are being mentioned to the left, and as per this particular previous information, we can just categorize them in the potential classes. Now we have identified or proposed a number of potential classes. So there are 6 selection characteristics that should be used as to consider each potential class for the inclusion in the analysis model. So the Code and Jordan has proposed these 6 selection criteria or characteristics. So number one characteristics is retained information. The potential class will be useful during the analysis only if the information about it must be remembered so that the system can function. Another characteristic is needed service. The potential class must have a set of identifiable operations that can change the value of its attributes in some way. Third characteristic is multiple attributes. During the requirement analysis, the focus should be on major information. A class with a single attribute may be useful during design but is probably better represented as an attribute of another class during the analysis activity. Fourth characteristic is a common attributes. A set of attributes can be defined for the potential class, and these attributes should be applied to all instances of the class. Fifth characteristic is the common operations. A set of operations can be defined for the potential class, and these operations apply to all the instances of the class. And the last 6 characteristics is the essential requirements. External entities that appear in the problem space and produce or consume information essential to the operation of any solution for the system will almost always be defined as classes in the requirements model. Now, let us pause here and apply these 6 selection characteristics to the list of potential safe home classes which we have previously drawn. So, to be considered a legitimate class for the inclusion in the requirements model, a potential object should satisfy all or almost all of these characteristics. So, let us apply the 6 selection characteristics to the list of these potential safe home classes as per this particular table. So here, to the left you can see the potential classes, and to the right you can see whether they are included into requirements model or not. Consider the homeowner as a potential class where it cannot be included into the requirements model. Reason being the characteristics 1 and 2 is being failed, though the characteristic 6 is being applied. So here the characteristic 6 is essential requirements. It is an external entity. It is an essential requirement, but characteristics number 1 retained information and the needed service. So homeowner doesn't retain any information currently and doesn't have any needed service. So if each homeowner had an individual password or was identified by a voice print, the homeowner class would satisfy the characteristics 1 and 2 and would have been accepted in this particular potential class. So this is possible by converting this rejection into an acceptance by making this information available. So this list is not all inclusive. Additional classes would have to be added or rejected to complete the model. So for example, a number and type are attributes of sensor. This is the number and types. These are the attributes of sensor. They cannot be classes. And master password and the telephone number may become the attributes of the system. So now next step is defining the attributes. Now we have identified the potential classes. Now let's define the attributes. So attributes describe a class that has been selected for inclusion in the analysis model. It is the attributes that define the class, that clarify what is meant by the class in the context of the problem space. Let us build two different player classes for professional baseball players in different contexts. In the first, the for playing statistics for a software, so we can include the name, position, batting average, fielding percentage, years played and games played might be relevant when in the context of playing statistics software for the professional baseball player and player as a class. So for the same player class, if we are developing a software for pension fund, then the average salary credit towards full ownership, pension plan options chosen, mailing address and others attributes which defines the player. So to develop a meaningful set of attributes for an analysis class, the following questions should be answered for each class. What data items fully define this class in the context of the problem at hand? For example, the class diagram for the system class can be is being shown over here. So this is a rectangle which has a three different compartments. There is a name of the class. Below the name of the class attributes are being associated, and below that there are various functions which are associated with this class. Now let us define the operations, one of the primitives for the this particular strategy of object-oriented analysis. So operations define the behavior of an object. Operations can be divided into four broad categories. Number one, operations that manipulate data in some way, like addition, deletion, reformatting, and selecting. And second, the operations that perform a computation. Operations that inquire about the state of an object, and the fourth, the operations that monitor an object for the occurrence of a controlling event. To select the operations, the grammatical parse is done and the verbs are isolated. For example, to identify the operations from the phrases, sensor is assigned a number and type, or a master password is programmed for arming and disarming the system. So here an assign operation is relevant to the sensor class. A program operation will be applied to the system class, and arm and disarm are the operations that apply to the system class. In addition to the grammatical parts, you can gain additional insight into the other operations by considering the communication that occurs between the objects. So let us consider the class diagram for the floor plan. So basically, for floor plan is needed to monitor the home. So for home surveillance, like we need to monitor and set up the cameras by making use of this floor plan. Floor plan consists of wall, and this wall consists of the wall segment and windows and the doors. So these are the window, door and wall segment is used to build a wall, and wall is a part of the floor plan, and the camera is placed within the floor, within that particular floor plan. So this is how the class diagram can be described. So we will see much more details, its operations and its attributes, and we can check the communication between these various objects and again come up with the different operations. One of the most important element is CRC model while describing the requirements model. So which is nothing but a class responsibility collaborator. CRC modeling provides a simple means for identifying and organizing the classes that are relevant to the system or product requirements. So Ambler describes CRC modeling in the following way. A CRC model is really a collection of standard index cards that represent classes. The cards are divided into three different sections. So first section, that means along top of the card you write the name of the class, and in the body of the card you list the class responsibilities and on the left and the collaborators on the right. We will see the details of class types, responsibility and the collaborator in coming slide. So this is an example of CRC model index card, wherein on top you can see the name of the class floor plan. There are various responsibilities associated with this, which defines the floor plan name, then manages the floor plan positioning. Here you can see this floor plan incorporates walls, doors, and windows. So wall is another class which is associated with this responsibility. Again, there is another class which that is camera, which shows the position of the video cameras and responsible and associated with the class floor plan. Let us see various class types. So the taxonomy of class types can be extended by considering the following categories. Entity class, which is also called the model or business classes, are extracted directly from the statement of the problem. These classes typically represent things that are to be stored in a database and persist throughout the duration of the application. Another type of class is boundary class. The boundary classes are used to create the interface, for example an interactive screen or printed reports, which are that the user sees and interacts with as the software is used. Controller classes manage a unit of work from the start to finish. So that is, controller classes can be designed to manage number one, the creation or update of entity objects, the instantiation of boundary objects as they obtain information from entity objects. Third, complex communication between sets of objects. And fourth, validation of data communicated between objects or between the user and the application. Controller classes are not being considered until the design activity has begun. Let us talk about responsibilities in CRC model. So there are 5 guidelines which are suggested for allocating responsibilities to the classes, which are as follows. System intelligence should be distributed across classes to best address the needs of the problem. That means concentration of intelligence can be checked against the responsibilities noted on the CRC card. If there are a lot of responsibilities on the CRC card, then there is a lot of concentration happening of various responsibilities. Then we need to check with if it is being concentrated only on one card, so we need to distribute it so that the problem will be resolved. So each responsibility should be stated as generally as possible. This guideline implies that general responsibilities like both attributes and operations should reside high in the class hierarchy because they are generic. They will apply to all subclasses. Number 3, information and the behavior related to the class should reside within the same class. So data and the processes that manipulate the data should be packaged as a cohesive unit. So encapsulation should be there. So information about one thing should be localized with a single class, not distributed across multiple classes. A single class should take on responsibility for storing and manipulating a specific type of information. So more than one classes should not do the same. Okay, so responsibilities should be shared among related classes when appropriate. A single class should take on responsibility for storing and manipulating a specific type of information. Let us talk about or discuss about collaborations. So collaborations identify relationships between the classes. Classes fulfill their responsibilities in one of the two ways. Number one, a class can use its own operations to manipulate its own attributes, thereby fulfilling a particular responsibility. Another, a class can collaborate with the other classes. So collaborations are identified by determining whether a class can fulfill each responsibility itself. If it cannot, then it needs to interact with another class and hence a collaboration. A responsibility named determined sensor status in safe home system is defined. So control panel class acquires sensor information from each sensor object. Therefore, the responsibility determined sensor status can be fulfilled only if the control panel works in collaboration with the sensor class. So to help in the identification of collaborators, you can examine 3 different generic relationships between the classes. Those are named as the is part of relationship, the has knowledge of relationship, and the depends upon relationship. So we will see each relationship in details in next slides. Now let us talk about these three relationship by making use of composite aggregate class. So all classes that are part of an aggregate class are connected to the aggregate class via an is part of relationship. The class player body is a part of player. The class player arm, the player head, and the player legs are all part of the player. So in UML, these relationships are represented as the aggregation. So you can see the symbol of aggregation over here. So when one class must acquire information from another class, the has knowledge of relationship is established. So the determined sensor status is a responsivity which is noted earlier is an example of has knowledge of relationship. The depends upon relationship implies that the two classes have a dependency that is not achieved by the has knowledge of or is part of relationship. The player head depends upon the player body as its center position is depend upon player body which is obtained via player. The player head is depends upon player body because its center position is required by the player head. So there is a depends upon relationship. Once the CRC index cards are being ready, then the CRC model is being prepared. The process review process of a CRC model is undertaken. So all participants in the review are given a subset of CRC model index cards. Cards that collaborate should be separated. That is, no reviewer should have two cards that collaborate with each other. All use case scenarios and corresponding use case diagrams should be organized into categories. A review leader reads the use case deliberately. As the review leader comes to a named object, she passes a token to the person holding the corresponding class index card. When the token is passed, the holder of the class card is asked to describe the responsibilities noted on the card. The group determines whether one or more of the responsibilities satisfies the use case requirement or not. If the responsibilities and collaborations are noted on the index cards cannot accommodate the use case, modifications are made to the cards. These modifications may include the definition of new classes or the specification of new or revised responsibilities or collaborations on existing cards. One of the important terminologies in class-based modeling is associations and the dependencies. So the two analysis classes are often related to one another in some fashion. In UML, these relationships are called as associations. Associations can be defined by indicating multiplicity. Multiplicity can be indicated this way: one to many to many, one to one. Then in many instances, a client-server relationship exists between two analysis classes. In such cases, a client class depends on the server class in some way, and a dependency relationship is established. In our previous safe home surveillance system, the floor plan class is defined by identifying a set of associations between floor plan and two other classes like camera and the wall. The class wall is associated with three classes that allow a wall to be constructed: the wall segment class, window class, and the door class, which is shown in this particular figure. In this figure, you can see the wall is being constructed using wall segment, window, and the door. There can be one or more than one wall segment to a particular wall. There cannot be window, or there can be many windows, more than one windows to a particular wall. There can be no door, or there can be more than one door to a particular wall. So this is association of these three classes with the wall, and the multiplicity is shown here over here. Now let's talk about dependencies. So dependencies are defined by a stereotype. A stereotype is an extensibility mechanism. A stereotype is an extensibility mechanism. In UML, stereotypes are represented in double angle brackets. For example, a camera object provides a video image to display window object. So a special password must be provided in order to view specific camera locations. Camera request a password and then grant permission to the display window to produce the video display. This can be represented as shown in the figure, where access in stereotype implies that the use of camera output is controlled by a special password. Here you can see the window class and the camera class. So this camera class requests a password to the display window, and once the password is being provided, the camera provides an access, which is an extensibility mechanism for the class. Let's talk about analysis packages. Various elements of the analysis model, for example use cases, analysis classes, are categorized in a manner that packages them as a grouping called analysis package. So the plus sign indicates analysis class name in each package. Indicate the plus sign preceding the analysis class name indicates that the classes have public visibility and are therefore accessible from other packages. A minus sign indicates that an element is hidden from all other packages, and a hash symbol indicates that an element is accessible only to packages contained within a given package. You can see over here a package for the game, online video game. So here you can see three different packages: an environment, rules of the game, and the characters. So in this environment you can see different objects which has a public visibility: tree, landscape, road, wall, bridge. All these are objects which are having a public visibility. Here the rules of games have rules of movement and the constraints on action, and there are various characters from the game like player, the protagonist, the one who is hero, the antagonist, the one is opponent, and there are someone who supporting role. So this is the package diagram for a particular online video game. Let us summarize the whole thing which we have learned up till now. So the class-based modeling uses information derived from the use cases and other written application descriptions to identify the analysis classes. A grammatical parse may be used to extract candidate classes, attributes, and operations from the text-based narratives. Criteria for the definition of class is defined. A set of class responsibility and collaborator index cards can be used to define relationships between the classes. A variety of UML modeling notations can be applied to define hierarchies, relationships, associations, aggregations, and dependencies among the classes. The analysis packages are used to categorize and group classes in a manner that makes them more manageable for large